Is it true that for a set A, the difference between A and itself is going to be the empty set? Now this should be a fairly trivial proof because it should make sense to you in your head. Like this is like saying something minus itself is going to be nothing. And that's true, right? If you take 1 minus 1, that's going to be 0. If you take 101 minus 101, that's going to be 0. If you take x minus x, that's going to be 0, right? Anything minus itself is just going to get rid of that thing and there's going to be nothing left. But what does this mean in terms of sets? Now, this is the first example I'm doing with the difference. Sometimes you could say, equivalently, you could say something like this, or I think the other way you could say this is this, I think. I'm not sure about this last one, but definitely the second one. Those are the other ways of saying this. And what does it mean in set theory? Well, when we're saying something like this, when we're saying something like A minus B, the set A minus the set B, we're saying that there's some elements in A and those elements are not in B. That's what it means to say something like this. So when we're saying A minus A, what we're really saying is that the elements in A are also not in A. Now this should sound off alarm bells in your head because that doesn't make any sense. This sounds like a contradiction. How could you have something be in A but also not be in A? So that should be a pretty big hint as to what the proof is going to look like for this. The other thing to note is that this is also an equivalence proof, which means that you have to prove that the right-hand side, everything on the right-hand side is in the left-hand side, and everything on the left-hand side is in the right-hand side. So let's go ahead and try and prove this because we can already see that obviously this is going to be true. So to start off, this is a for all proof because we are looking at any set A. It could be like, well, yeah, it could literally be any set subtracted from itself. So this is a for all proof, which means we have to start it with a let. So we say let, I need a better marker. Let's use this one maybe. We can say let A be a set. Now remember, you don't have to also suppose the empty set because that's like saying let 1 be a number, right? You don't need to say that. We are assuming everyone who reads your math proof knows 1 is a number, the same way we assume everyone knows the empty set is a set. The reason we assume A is because this is like saying let x be an integer, right? If I didn't say this and I started using x, you'd be like, well, what's x? Is it a real number? Is it a function? Is it a set? So we have to define A, but we don't need to define the empty set for this very reason. Okay. So where do we go from here? Well, first let's take the first case. Let's first prove that everything on the left-hand side is in the right-hand side, or the following. Okay, so the first thing we want to prove is that A minus A is a subset of the empty set, or basically this only can contain nothing, is what we're saying, right? So how do we start? Well, we want to start by, of course, saying A minus A, and we want to get to the empty set somehow. So what can we say? Well, first we want to assume that for something to be a subset of something, that means any element here, like x, has to also be an element of our goal, right? But because we're dealing with the empty set, you cannot have any element x in the empty set. So we have to actually get from here and show that if you have any element here, you cannot have that element be in the empty set. So this probably is going to be a contradiction. But let's go ahead and see. Let's first write down what this means. This means, as I've said, that x must be in A and x must not be in A. Now this is immediately going to set off alarm bells. This cannot be true at the same time. So because you cannot have an element be in something and not be in something at the same time, this is simply going to be false. It means that our assumption here cannot be true. So because this is a contradiction, this creates a contradiction, the opposite must be true. So it must be that there are no elements in A minus A, which then leads to us seeing that A minus A legitimately has nothing in it, which means it's going to be the empty set, right? So let's go ahead and put that into words. Okay, so to put this into words, let's start by first clarifying this is going to be a proof by contradiction. Okay. So what are we going to do? We're first going to suppose what's not going to be true. We're going to suppose that x is going to be an element of A minus A. Fantastic. Then we want to unpack what that means. We say that then x is an element of A and x is not an element of A. However, this cannot, or we'll just say this is a contradiction. Now, usually it's not good to just say it's a contradiction and move on, but I feel like this is so fundamental that there's nothing else I could say apart from repeating this. Or maybe I'll just say, since an element cannot be simultaneously in and not in a set. Fantastic. Meaning our original assumption cannot be true, meaning x cannot be an element of A minus A, so A minus A is a subset of the empty set. Is that even possible? I'm trying to think, like proving the other way around doesn't seem to make sense. Can I just actually do I even need to do cases for this case, even though it's an equivalence? Give me a moment, I need to think about this. Okay, so I clarified it, and yes, you can definitely say that something, you can make the statement something is a subset of the empty set. That's not mathematically wrong. So this should be fine for a case. So yeah, we've proven that A minus A is a subset of the empty set because A minus A can't have anything in that set. So now let's prove the second case, that the empty set is a subset of A minus A. Okay, so this time we're starting on the other end. We want to show that when you have an element here, right? Because to show something is a subset of something, everything here must be here. So we want to show that any element x in the empty set will also be an element of A minus A. Well, immediately we know that this can't be true. You can't have an element in the empty set, so it must be that x is not in the empty set. And where can we go from here? If x is not in the empty set, would this be a vacuous truth? I'm thinking, because there's no like steps you can write out here with arrows that get you to here that I can think of, other than just saying, well, yeah, if you have nothing, is nothing always going to be an element of that? Maybe we can try. We can try saying something that this means x cannot be an element of, no. It's a little difficult to prove the other direction. Maybe if this is a vacuous proof, then you can just probably jump to here, but I'm not sure about that. I'm thinking maybe we can use the fact that the empty set is always a subset of any set. That probably seems right, since it's true in sets that the empty set is always a subset of anything. It can be anything here, right? Could be A union, so on and so forth. The empty set is always going to be a subset of any set. Yeah, I think we can use that logic. We can say that because the empty set is a subset of any set, this will always be in any set, that this is automatically true. So I guess that is a vacuous proof, I think, or a vacuous statement. Vacuous truth? I don't know. The point is that because this is always going to be a subset of anything, this is obviously going to be true. Okay, let's put that into words. So we can say, since the empty set is always a subset of any set, then it follows the empty set is a subset of A minus A. Yeah, okay, I think, that should make sense. If it doesn't, grill me in the comments, but that should make sense. So we've shown both directions are true, so now we can just write our conclusion. Maybe I need to get a better blue marker. Ooh, there we go. This one is nicer. Okay, we can say, in conclusion, since A minus A is a subset of the empty set, and the empty set is obviously going to be a subset of A minus A, then A minus A is equal to the empty set. So there we go. We have proven that this is in fact going to be true.